stage, on this stage, there will be more on the other stage, is by Dr. Todd, who is an AI and optimization consultant with Fujitsu. And his talk is titled Quantum Algorithm for Molecular Property Characterization. So that means we will stay in computational chemistry. And he will be talking about experiments on quantum algorithms for solving Schrödinger equation to characterize molecular properties using examples of several trial molecules. Mr. Law, thank you so much for being with us. The floor is yours.
Yes, thank you very much. And the previous talk sounded fascinating, and I want to check it out myself after my own talk is done. But yes, thank you, David. So my talk is titled Quantum-Inspired Computational Chemistry for Materials Science, and I am with Fujitsu in Vancouver, Canada. So I want to introduce a little bit about the companies behind this, the vision we're working towards, the problem statement, an experiment that we did, and the results from that experiment, and some ways that we can move forward from that. So Fujitsu, you probably already heard about it from the previous Fujitsu presenters. However, in this presentation, we had a partner in our collaboration, and that company is called OTI Lumionics. OTI is a startup in Toronto, maybe more now of a scale-up that was established in 2011, and their focus is on key materials in displays. And they take a computational approach to identifying new candidate materials for their products. And they use quantum and quantum-inspired or quantum-esque simulations to do that. And they've received funding from large industry players like LG and others. So if you've bought a cell phone in the past 10 years, chances are that some of the molecules in the displays you're using are similar to the ones that OTI is investigating. On the Fujitsu side, the product that we're leveraging is called the Digital Annealer. And I think you heard about that from the other Fujitsu presenters, and I'll go into that a little bit more later on. Our vision is to utilize quantum computing technology for computational chemistry, specifically to characterize new molecules for batteries, solar panels, catalysts, polymers, semiconductors, alloys, pharmaceuticals by rapidly, efficiently, and accurately solving the Schrödinger equation on large molecules. And the problem we're specifically trying to solve is the Schrödinger equation. And by solving the Schrödinger equation, you get the wave function. And from the wave function, you can get the energy levels. And from the energy levels, you can get the material properties. And I know it's not as simple as this. There are other things that are important, like the structure and the vibrational spectra, but this is a good starting point. And we want to find solutions that are sufficiently accurate, that use reasonable quantities of compute resources, be they memory or CPU hours or what have you, that apply to meaningful molecules, and do this all within a reasonable duration of time. And our approach is to use our quantum-inspired computing technology to solve this problem. It's worth noting that the Schrödinger equation is naturally a hobo, or a higher order binary optimization format or of objective function, and we can convert it to something called a cubo, which is a quadratic unconstrained binary optimization. We can convert it quite easily. I think there's a word missing there. And this allows the problem to be solved on a digital or quantum annealer. So this is sort of the first step in our process. It's also worth mentioning that quantum computing is a good approach, and many industry players have identified quantum chemistry as a good first problem for quantum computing. And of course, many of us know that when Richard Feynman first proposed quantum computers, or he imagined them, he was inspired by quantum chemistry in the first place. So let's use that natural phenomena as a computing, as a computing resource. And there's the reason for his insight and the reason for this application is the isometric similarity between quantum physics and quantum computing. And moreover, the number of qubits required to solve a meaningful molecule is not huge. And therefore, players like Google, IBM, and others have made attempts and published results to solve the Schrödinger equation in various ways. And one of the more famous Google's claim is the quantum supremacy back in late 2019, and then more recently IBM, an update, which I'll discuss as well, and others. So how does Fujitsu approach this? Well, our answer to optimization is something called the digital annealer, and it's a technology for solving all sorts of optimization problems, including logistics, finance, and material science, which we're talking about here today. At its heart, it's a chip, a traditional CMOS chip, gate-based approach that is implemented in silicon, and it's exposed through surrounding software, meaning APIs, and we offer it with consulting services to map customer problems into solutions. And at its heart, it's available as a cloud service, although we don't necessarily offer it directly today in that form to customers. Just to quickly explain the features and benefits of the digital annealer, it leverages parallel execution, which delivers speed. It uses an intelligent search algorithm, specifically the Metropolis Hastings algorithm, to escape local minima, and the full connectivity and high scale precision together offer the benefit of handling complexity. And together, all of these things allow the rapid finding of optimal solutions to large, complex problems, which is ultimately what we're trying to do by finding solutions to the Schrodinger equation. Our partner in crime, OTI, their contribution to the story is something called IQCC, which is the Iterative Cubit coupled cluster algorithm. And it's another approach to solving the Schrodinger equation. You may be aware of the various families of approaches to solving the Schrodinger equation, the oldest of which is called Hartree-Fock, succeeded by something called DFT, or density functional theory, which is really a family of approaches. And then comes coupled cluster and a number of other approaches. A coupled cluster is admired for its ability to achieve accuracy, and sometimes it's referred to as a gold standard. And OTI's incarnation of this is IQCC, so iterative, meaning repeated in nature, and qubit, so it can map it to a quantum algorithm. And there are more details available through papers that can be freely accessed from archives, such as the one shown here on the right, for anybody who would like to dig more deeply into the details of that algorithm. Now, basically, what did we do together? Well, it's a bit of a Reese's peanut butter cup approach, the chocolate and peanut butter, if you will, where we combined the Fujitsu digital annealer and its various technologies together with OTI's IQCC algorithm to iterate in finding solutions to the Schrodinger equation. And they both employ a set of strategies to do that in tandem. And we built this implementation or integration, if you will, between IQCC and the digital annealer, and then applied it to a few different molecules. The first of which was nitrogen, or N2. It's relatively small, so 14 electrons. And the purpose was to show that the solution works. And we also fortunately have a ground truth in the form of FCI, or full configuration interaction results, to compare against. And that was our first experiment. I'll go into more detail there. The second molecule we tried it on was called IRPPY3. So this is a larger molecule with 320 electrons. It's relevant and familiar to OTI. It's because it's used in OLED displays. And we also happen to have experimental gap results from University in California. I believe it's Professor Chris Thompson, who's published results on the energy levels from actual molecules and using X-ray crystallography to get their lab results. And the purpose of this molecule in our experiment was to show that our solution is valid on a market relevant material. And then based on the results from that second molecule, we went and applied it to our third molecule, which was FMOCO, which is a cofactor. So the CO here is not for cobalt, it's for cofactor. And it's a large molecule with 374 electrons, if you can call that large. It's an enzyme used to produce fertilizer, which is, by the way, the Haber-Bosch process that's been around for 100 or so years. And it's an energy intensive process. So it's energy intensive and uses around, so this says 1.2%, but some estimates are as much as 2 to 3% of all of the world's energy consumption used in the process and the production of fertilizer. However, the reaction by which fertilizer is produced is not thoroughly understood. and therefore computational chemists have attempted to try to solve it. And therefore, even quantum computational approaches have been tried to apply to this problem as well. So it's a very interesting and relevant molecule. And we want to tell you more about the results from each of those molecules. So for nitrogen, essentially, we demonstrated functionality. And I've abbreviated the slides I'm showing here. I have sort of a bigger version of this deck that shows the numbers, the numerical results, and also the results from classical computational methods and so on. But basically, we were able to validate that our results are very close to, and in fact, slightly better than anything else out there. So, but it's more, this is not the most challenging molecule. It's not very large or complex. However, it is still larger than the molecule that IBM has announced results regarding this. So their news in 2021 of May in a press release claimed that they solved lithium hydride, which has only 5 electrons, and the press release said it took 9 hours to solve it. And that was an update on an older press release from 2017 where there was a claim to solve it in 45 days, and they used seven qubits. So that was an interesting piece, or sort of a starting point. The next molecule, to go a little more deeply, IRPPY3, so that OLED display molecule, we were able to show that our results were better than TD-DFT. So I mentioned density functional theory. This is a variant of that. And more interestingly, we noticed that the digital annealer was able to flip from a triplet state to a singlet state. So this has to do with the allocation of electrons and their spins to the different orbitals, et cetera. And we were able to escape a local minimum. And ultimately, this meant that the digital annealer was able to steer, quote unquote, the search for solutions more broadly rather than being limited to a local search area. And this suggests that the combined solution may have unique value, especially to characterize compounds with complex or esoteric orbitals. And this insight, if you will, led us to a desire to try the combined solution on another complex molecule, which is FUMOCO. And then FUMOCO, the last molecule. Also, we have numerical results, which we could show you if you're interested in offline. I will provide my contact details at the end of the presentation. We were able to find solutions which are violations of the Outflow Principle. Now, the Outflow Principle is a guideline, if you will, that states that the lowest orbitals should all be filled before filling higher orbitals in molecules. But it's more of a guideline. It's not a hard and fast rule, and therefore it's okay to violate or have exceptions to the Outflow Principle as long as the total energy is less than Aufbau conforming states. So basically what we found for FUMOCO is that there are valid and lower energy exceptions or solutions to molecules that are violating this principle. And they're closer in energy to the global ground states than previously realized. And this suggests that the excited states are much closer in energy and have a different order than the current literature suggests. And this has implications for understanding the transition states, so between the ground state and the excited state in a chemical reaction, or the pathway between the two states, if you will. And it also demonstrates that though even with CAS SCF, the assumed CAS CI may not be the lowest ground state, even with the same electron and spin states. So this is high, deep chemistry talk, but what it really means is that we've been able to provide insight into the structure of this very interesting and relevant molecule through our combined approach that would not have been achieved otherwise, and can lend or inform or inspire, if you will, potential new catalysts, which could be more energy efficient or suggest a different way to something to do the equivalent of the Haber-Bosch process. And by the way, this has much more, much deeper ramifications than simply the production of fertilizer. The Haber-Bosch process enabled the first hydrogen revolution, as I said, more than 100 years ago, which enabled the creation of fertilizer to essentially feed us all, the growing population of the world. But the world's also looking towards a second hydrogen revolution to decarbonize. So very much connecting with the previous presentation. If we can have better insights into the molecules that are used to produce, for example, ammonia or cyclohexane, excuse me if I get the name wrong, but or other hydrogen carrying liquids, this could enable a transition to a carbon reduced economy. I don't know if I can say totally carbon free, but this has super relevance for the energy industry as well. Let's just say that. Okay, so here, what is the time here? 6:30, 3:30 in Germany. I think that's the end of it. And my 15 minutes of fame are up. Feel free to contact me afterwards. My email address is here if you'd like to go deeper on this topic. And I guess we have a few minutes, David, for any questions that might be out there.
Todd, wonderful. Thank you so much for giving this talk, also for making it kind of more accessible also to non-chemistry background audience. I think they were super relevant and helpful. Thank you for this. One question I would have, also looking at what you explained, giving the molecules that you selected for your work so far. Maybe question one, how did you select exactly those? If you're not too familiar with the kind of chemical properties that surround them, that would be a question I have. Question two, which molecules could be next and why?
Yeah, thank you. Yeah, so I'm an electrical engineer and a computer scientist by background. I'm not a chemist either. And I have a bit of a joke that I've been avoiding chemistry my whole life, but it keeps coming back to haunt me. So we really did it in consultation with OTI. They are really the experts on the chemistry side. But you could see there was, of course, the nitrogen was the proving functionality stage, right? We just chose that as a baseline, like something simple. We had a ground truth. We could confirm it works. That was the basis there. And then, we went to IRPPY3 because it was known territory for OTI and their OLED world. And then FOMOCO was also based on OTI's recommendation and its relevance towards both fertilizer and the energy industry. Now, in terms of where to go next, that's a really, really interesting question. And last year, I put together a consortium of universities and companies to make a proposal towards Horizon, the European grant funding agency. And it was a joint program between Canada and the EU. Unfortunately, our proposal was not accepted, but we learned a great deal, and we actually had a roadmap of molecules that we wanted to move through. And that had about 8 or 9 different molecules on it. And it started off with some very simple molecules and graduating towards water. And I think methane is basically the boundary or the limit of what's possible with classical computational techniques. So methane is a fairly well-known molecule. And then beyond that, there's sort of the unknown territory. And there were 4 or 5 interesting molecules that were on our roadmap. And FOMOCO was one of them, but another one was cisplatin. Cisplatin is like a scaffolding molecule for medications. And there was a third molecule. It's also another enzyme or a molecule. The name escapes me, but I could provide that offline if anybody's interested in more details on the roadmap of molecules that we would have liked to have tried in that.
Todd, thank you so much for this also very comprehensive answer. I think I very much also have an idea now. Thank you for this. Because again, I'm not from a chemical background, so this is super helpful to also see the impact. Maybe last question, and then it's time for us to also close this stage. Maybe what was your most significant learning looking back at this project, looking back at the partnership as well between you and OGI?
Thank you. Yeah. For me, the deepest learning is really the diversity within this space and how you encounter specialists who are extremely good at their job. They spend 20, 30 years in a particular area and they know it super well, but they have only like a superficial understanding of the areas outside. So there's a large collection of individuals who are excellent at their particular area, but they have limited knowledge outside of that. And this applies both on the computational side between the classical and the quantum computing part of it, as well as the chemistry side between academia and industry people, as well as between pharma and material science. And then with material science, the domain even stretches to specific kind of areas like energy or polymers or what have you. And then even within that, it's diverse yet again. So it's almost like there's a multitude of universes, of worlds, that it's just each person lives in their world, and they kind of have only a vague awareness of the worlds beyond their kind of day-to-day life. So it's just the depth and breadth of the diversity is really is one of the biggest challenge here. And that makes the cross-disciplinary aspect of it rather challenging, but also very fascinating and interesting and fun. I hope that answers your question.
All right, Todd, thank you so much. It does indeed. I think this is also like a wonderful, beautiful takeaway in the sense that combining this diversity together and then seeing where you can go, I think this is quite enormous, and this is the future in a sense. It sounds very interesting. Thank you for being with us today. All right, Todd, again, thanks. See you next time maybe. And I think then it's time for me to wrap up this stage, to maybe give a short kind of thank you note to all of you for watching on stage Bob. We talked about financial services. We talked about rather theoretical ideas, which were super interesting given kind of their potential also impact on quantum technology as of today and in the future. We looked into different industry domains as well as sustainability in the future and today. This was also, I think, very thought-provoking for many of us. And so next and last but not least, I would again like to hand back to Stage Alice. So I invite you to go to Stage Alice, where we have Peter Vermaas from Delft University of Technology talking about the societal impact of quantum technology. What are the benefits? What are the possibilities, the opportunities? What are maybe the risks on the other side? And discussing these questions, of course, is essential when we have a discourse about technology. So I invite you to go to the other stage and enjoy the rest of the conference. Thank you so much. Yes.